So last time we left at this spot where we were looking at the heat equation on a rod with a source term given by S, and we ended up concluding that this is the system of equations that we obtain for a discretization for n points, an arbitrary number n, and we went ahead and did some examples with the Thomas algorithm, not specifically for the heat equation, but today I want to go over using the Thomas algorithm specifically for the heat equation. So we're going to go ahead and program this system of equations in Python and then define a source term. We'll pick an arbitrary source term, maybe a Gaussian distribution where it's kind of zero everywhere along the rod, and maybe at the center the volumetric heat transfer is peak and then goes down to zero, so there's some heating in the middle of the rod. And then we'll go ahead and solve it with the built-in routines in Python, direct solve or A inverse, and then we'll call the Thomas algorithm just to show you how this works. Okay, so let's go ahead and open up a Python notebook. And I'm going to create a new Python notebook over here. Okay, so we'll just call this heat equation in class. Let me increase this size a little bit over here. Heat equation in class. Okay, oops. Typo over there. Okay. The usual, we want to import a bunch of things. Right now, you know what these are. We want to import numpy as np, and then from numpy we need the diagonal function, import diag, and we need the solve function from numpy.lin algebra import solve. We need the solve function. Now, I want to do some plots over here, and for those who haven't done plots in Python before, let me remind you that we do this with the matplotlib library. So import matplotlib.pyplot as plt, just a nickname for matplotlib. And then there's a little trick we need to do in Jupyter Notebooks. We need to make matplotlib inline. And there's another trick that I do. You certainly don't have to do this, but it's a little trick I learned over the years that produces really high quality vector graphics in your notebooks, and it's given by this little magic. Just copy it. If you like it, copy it and use it, or just type it up and use it in all your notebooks. Okay, great. We're done here. If you remember in the problem, in the heat transfer problem that we looked at, so let me pull up the slides again and remind you. The first step that we did was to discretize, to split the domain into a finite number of points, right? So given a distance L, we wanted to create a set of discrete points, and then I told you you can do this with linspace, right? So let's go ahead and define our domain length. We're going to call this L equal 1.0, of course. And let's define the number of points n. Let's say we want to do this for the 100 points. Of course, as we test, we're going to do this with 5 or 10 points just to make sure things are correct. Now we define delta x. Remember, delta x was given by, now delta x is the number of intervals and n is the number of points. There is always one more point than there are intervals. Again, if you look at the slides over here, for example, you have 1, 2, 3, 4, 5 intervals, but 6 points. 1, 2, 3, 4, 5, 6 points. So delta x is L over n minus 1. That gives us delta x. And then we define our linear space, which is essentially the coordinates of these points, and say mp dot lin space. We want to go from 0 to L and put n number of points. So let's say if n was 10, if we print x, we should go from 0 to 1, correct? And if we put 100, you're going to get the same thing, okay, just with more points. Okay, great. Now we defined x. Let's go ahead and define the source term. And like I said, I was going to create a Gaussian source term, and essentially what the Gaussian is just like a bell curve, right, where you have a peak somewhere at a given point, so this serves as a really nice source term. So define, let's call it source. Now what does the function source need? It just needs x, right? It needs a location along the rod, and I want to return a Gaussian. And if you don't know how to do the Gaussian, just take this for granted. This will be given to you, and this would be an exponential function that decays, that looks like, x minus x0 squared over some standard deviation. Okay, so we'll define those values in a second, and let's say sigma is equal to 0.1. You can for sure define source and pass arguments for sigma and x0. X0 is going to be the location of the mean or the hump, where the hump is, and so let's say x0 equal 2/3. Okay. And to verify that this works, to have a look at this, you simply plt.plot. You want to plot the source versus x. So we give the py plot x first, the x-axis, and then source as a function of x. And then you see this nice plot. So this is showing you as we go along the rod from 0 to 1, we have a lot of heat being added to the rod. Now the units may be confusing to you over here right now, but so those numbers will be given to you. We just want to make sure that they make sense. So obviously if you change the standard deviation, it becomes much thinner, so there's more concentrated heating along the rod. If you make sigma larger, it's going to be more evenly spread. And you can normalize this coefficient over here. I'm not going to worry about this. If you change this number, let's say make it 0.5, it's going to move the peak to the middle. Okay, I'm going to keep it as is. All right, this is good so far. Okay, so now let's go ahead and define the characteristics for our problem. If you remember, our problem was defined by temperature at the left and a temperature on the right, and the source term, of course. And so let's go ahead and create those. So TL is, say, 300, and T right, let's say, is 350. Okay, and for the thermal conductivity, that number K, I'm just going to use a number that I know by heart, and that's 1e to the minus 5. Okay, and now we can construct our diagonals. So if you remember the form of the matrix, we have -2 on the main diagonal, and then we change the first and last entry, and then 1 on the first lower diagonal, except for the last entry it's 0, and then 1 on the upper diagonal except for the first entry. And you see how S and K and delta X show up on the right hand side. Okay, so let's go ahead and start building those. So we start with D, and then the way I'm going to build this is create a NumPy array of 1s and multiply that by -2, so that gives me -2 everywhere, and p.1s. How many entries? We need n entries, right? And then D0 is going to be 1.0, and D -1, so that's the last entry, is going to be 1. So you see these two entries over here, 1 and 1. Okay, so that's the main diagonal. The lower diagonal is np.1s, so all 1s. How many entries? n-1 entries, right? Because it's 1 entry less. And for the lower diagonal, it's the last entry that's 0. And if you look, this is the lower diagonal, it's all 1s except for the last entry. And then the upper diagonal, same thing. Let's just add a few cells over here. So upper diagonal is np.1s n-1 similarly. And upper diagonal 0 is 0.0, right? Because it's the first entry over here. Okay. Now, this is all you need for the Thomas algorithm, but because I want to try the built-in solvers, I'm going to go ahead and build the matrix, the full matrix A, and that's going to be A equal lower diagonal -1, which is located -1, in terms of the ordering or the indexing of the diagonals, plus diag, main diagonal at 0, plus diag, upper diagonal at 1. Okay, And you can print A if you want, print A, and this is what it looks as expected. You can change this number over here just to get an idea, be able to see the full matrix. Okay, this is great. Now, next we need to build the right-hand side. Build the right-hand side, the B vector. And B was equal to minus delta x squared s over k, except for the first and last entries. Okay, so B is minus dx times source term at x. Now remember, source at x is an array, right? It's going to give you s0, s1, s2, and so on, over k. And we need to fix the first entry and call it TL, and the last entry and call it T right. So this should be called, yeah, I'm calling it T0 over here, and TL. So the nomenclature, there's a typo over here, and that obviously needs to be fixed. Okay, so now that's fixed over here. Let's go ahead and okay, so now we have the right-hand side. And finally, to solve this system of equations, solve using built-in solvers. Method 1, use the solve routine. We just simply call the solve routine. We say T is equal solve. Now what does the solve routine require? Coefficient matrix A, which is A, and a right-hand side B. And that should give us B. That should give us the temperature. So how do we do this? How do we look at this? We just simply print. Now remember, T is, we're going to have as many T's as there are X's. So if we plot, if we want to plot plt.plot, if we want to plot T, we can just plot it versus X, and that's what you get. Okay. As expected, the peak temperature is going to occur at the peak where the heat addition is being added. Okay, that's great. Now you can use another method where you could do the A inverse. Okay, and then you say A inv is np.lin algebra.inverse A, and then you say T. Let's call this method 2. Method 2 is equal to A inv. Now the solution in this case is A inverse times B, and the dot product you use the at symbol, and then plt.plot xt method 2, and then we should expect the same answer. Okay. Now finally, with the Thomas algorithm, in the last lecture we copied and put in the Thomas algorithm into one of the cells in the Jupyter notebook. I'm just going to copy and paste it over here. Remember, it takes a lower diagonal, main diagonal, upper diagonal, and a right-hand side. And note what I did over here. I passed those with different names so that I could make a copy, and I don't modify the original arrays. If you remember the last lecture, we noticed that when we pass the arrays by reference, they're going to be changed over here in this routine. We don't want the principal arrays to be changed, so we pass those, we give them just a different name here, and then we make copies, and then we just kind of work through and then return X without having to modify all the diagonals. Okay, and then T Thomas or T Thomas is equal just simply Thomas. What does the Thomas need? It needs a lower diagonal, a main diagonal, an upper diagonal, and a right-hand side. And then plt.plot xt Thomas, and then there you go. Now, obviously, if you add more points, you're going to have a better looking solution. Let's say do 200 points, and then you're going to see how the temperature profile looks. Now, an important thing to note and make sure of is that you satisfy the boundary conditions. Notice here at t equals 0, grid, I'm going to create a grid just to help us. At x equals 0, my temperature is 300 as expected, and it's 350 on the right-hand side. You can play around with the temperatures. You can play around with K. Again, the higher the thermal conductivity, we said there's going to be faster heat transfer. So if we try to change K, look at that. It pretty much distributed the heat very, very quickly across the entire rod, right? We put a very high conductivity. If we put a very low one, what is going to happen? It doesn't change much, but look at the heat over here. It's not being dissipated. It's like 35,000 degrees, which really doesn't make sense in this case. But anyway, you can see kind of what you can do with this. In reality, this source term, the way I put it here, is unphysical. I would need to properly normalize it and make sure that the numbers make sense so that you don't produce crazy temperatures. But in the end, this is what you can do with this method, and you can plot the Thomas on top of the other method. Let's say, give it a symbol O, and then X, and then T method 2. And then you can plot them on top of each other and see that they're just really on top of each other. And that's not surprising because the Thomas algorithm is in direct solvers. It's going to give you the exact answer with round-off errors, but it's going to give you the exact answers compared to A inverse or the direct solve method. It is a direct method. And that should essentially cover this. In your homework, what you will do, you will change the number of points n, but then you're going to have to compare how fast Thomas is compared to using A inverse and using solve.